All right, hi Wheaton North chemistry students. Today I'm speaking to you from the secret Wheaton North Trophy Vault about strong versus weak acids and what's the difference between those. All right, so looking at our titration lab, you guys did a bunch of calculations and you figured out that theoretically the calculated value for the sulfuric acid, we calculated that we would need about 40 milliliters of the base to neutralize that acid. And then for the acetic acid, we calculated that we should need about 20 milliliters of the base to do that. Now, the problem is when we did this, is that if you noticed, our numbers were off, and they were especially off for the acetic acid. Okay, we calculated that we needed, I think, 20, and I think a lot of groups probably ended up with only needing 8 or 9. So why? Why is there this big difference in percent error? And the reason is there's one other variable that we haven't talked about yet, and that's about the strength of acids, if they're strong versus weak. And that has a huge impact on when our acid bases come to that neutral point. Now, what a strong acid is, in a strong acid, all of the hydrogen ions leave the acid and join the water. So what this animation is showing you here is we put some hydrochloric gas or hydrochloric acid into solution here, and what you'll find is all of the H's and the Cl's dissociate. Okay, is that they're splitting apart, so that the hydrochloric acid, it's releasing all of those hydrogen ions into the solution. That's what makes an acid a strong acid, is if it's releasing all of those hydrogens. Now a weak acid, this is hydrogen fluoride, we put that into solution. A weak acid, only a few of those hydrogen ions leave the acid and join the water, as you can see by this animation. So we put those HFs in there, and then after a certain amount of time, only a small, and you can see right there, there's the ones floating around, only a small amount of those H's are leaving, or the hydrogen ions are going into solution. That makes it a weak acid. Okay, so with that definition or that idea, look at these two things and see if you can tell which one of those is the weak acid. Okay, now if you said beaker B, that's right. And why is that one the weak one? That one is the weak one because, again, you can look here, beaker A, all of the acid, the ions, the hydrogen ions and the negative ions, they've split apart. This one released all of its hydrogens into solution. That means it's going to be the strong acid. This one, you can see some of those are still connected. Only some of those hydrogen ions were released into solution, meaning that that is the weak acid. Okay, look at these. See if you can tell which one of these is the strongest. Okay, now if you look at these guys, you're kind of looking for these where the hydrogen's been released and then picked up onto another one. And if we compare these three, you can see that this one over here has a lot more of the hydrogens have been released, meaning that this is the strongest acid for acid C. Okay, now relating that back to our lab, let's look at this. We had the sulfuric acid and we had the acetic acid. Now for these, the sulfuric was the strong acid. Now this one, you should have been pretty close or in the ballpark of that 40 milliliters of base to neutralize that acid. And the reason is that sulfuric acid is a strong acid, so it's releasing all of its hydrogen ions into solution. Okay. Now the acetic acid, on the other hand, this one, because it was a weak acid, it did not release all of those hydrogen ions, and as a result, it took much less base in order to get it to neutralize, because there weren't as many of those free hydrogen ions floating around in there. Okay. Now here's just another example. Look at these two. Which is the weak acid? This one. So remember, again, weak means that not everything is being dissociated or it's not being released. This one, the HCl, you can see everything is split apart. This one over here, you can see that this one has only released one hydronium ion. Okay, and everything else is still kind of staying together. Look at these two. Which one's the weak? Yeah, this one over here. Again, look here. This one on the right side, this one has released all of the hydrogen ions into solution, and this one on this side has only released a few of them. Now in reality, most acids are weak acids. There's very few. I think there's 6 main strong acids. So the majority of acids out there are weak acids. So that's what we're really what we're dealing with here. So again, look to see how does this concentration of these two things compare. Okay, now if you look at this, the concentration is going to be the same. These guys, I think, each have about 7 each. Okay, and that's going to be important in a minute, because the key idea here is that concentration is not equal to strength. For a long time, you guys, if you have iced tea or Kool-Aid, or if your parents drink coffee, maybe you do, you talk about this is strong Kool-Aid, or this is really weak Kool-Aid, or this is strong coffee, or really weak coffee. And what we're really talking about when we're using those terms is, in that instance, you're talking about concentration, how concentrated it is. You have to break your kind of brain of that thought process when we're talking about acids and bases, because concentration is different than strength. Okay, pH is talking about how concentrated the acid is, and strength is not talking about that. It's not how concentrated. Strength, remember, is how many, if it's releasing all of its hydrogen ions or not. That's a big difference between these two ideas. Okay, so the pH doesn't tell you if an acid is strong or weak. It just tells you how many there are. Okay, pH is concentration, how many there are. That's different than the strength. Okay, so if we look at these pictures right here, this could be a dilute strong acid, okay, and this could be a concentrated strong acid. So again, if it's releasing all of its hydrogen ions, that's a strong acid, and it can be dilute or concentrated, one of those two things. Or you could define this as a dilute weak acid. Maybe this one did not release all of its hydrogen ions, and you could have it be dilute, meaning it's a low concentration, or it could be really concentrated, going the other way, with lots of the ions in there. Okay, so to get the same amount of hydrogen ions, you need more of the weak acid. Okay, so again, think about that. If I want to have the same amount of hydrogen ions, I'm going to need more of the weak ones in order to get it to be the same as that strong one. Okay, so here's just a little image showing 4 different beakers. Okay, and we've got these hydronium ions, and we're really going to be comparing these to see which one is dilute versus which one is concentrated, and then comparing strong to weak. Now the first thing I would say is, when you're looking at these pictures right here, is to figure out, all right, dilute, remember, is a low concentration. Concentrated means it's a high concentration, right? So if we're looking at all of these beakers, I think it should be pretty apparent which one's dilute, which 2 are dilute, and which 2 are strong. See if you can figure that out. All right, so if we look at these right here, these are more dilute, right? There's fewer of them, so they're going to be dilute. Concentrated, there's going to be a higher number of them. So you can see here we're dealing with 6s and 4s versus only 3s and 2s. So which beaker is a dilute strong acid? Okay, look at this one. So these 2 are dilute. Why is this one strong? Well, look, this one is, again, it's released. It's totally dissociated. We have the A's separate from the hydronium ions right here. Whereas over here, we only had these 2 are still together, and then here we have the hydronium ions separate. Okay, so which one is then, so that's a dilute strong acid, beaker C. Which one is the concentrated strong acid? So look up here. Which one of these 2 is concentrated? Yeah, beaker A is, right? Because again, you can see these guys have totally dissociated. We have hydronium ions, as well as the A's totally have separated themselves. Okay, now going the other way, dilute would be the dilute weak right here, because again, we haven't dissociated all the way, and it's a low concentration, and that means beaker B up here is going to be our concentrated weak acid. Okay, so it hasn't totally dissociated, but there's a lot of them, higher concentration. All right, here's a little short video that'll wrap up the concept for you.
Strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, HA, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion A- and a hydronium ion H3O+ form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A-, so the final hydronium ion concentration is much less than the original acid concentration. Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from HA to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no HA. As before, the moment the acid molecules make contact with the water, proton transfer from HA to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it, and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of HA and very low concentrations of H3O+ and A-. Therefore, the acid